Close your eyes for a second. Now imagine you could erase one object from the universe. Not break it, not move it, not melt it. Erase it. The chair under you, the phone in your hand, the walls, the floor, gone. You might think the hard part is imagining the object disappearing. It is not. The hard part is imagining what is left behind. Because when people say empty space, they picture a quiet stage, a blank background, a harmless nothing. But the most shocking fact about reality is this: what you call nothing is doing the most important work. It is the invisible reason anything can feel solid. And that is why today's question is so strange. Why does reality look solid at all? Why can you not slide your hand through a table like it is fog? If everything is made of atoms, and atoms are mostly empty, then why do you feel hardness? Where does solid come from? Early quantum physicists watched classical common sense fall apart at the atomic scale, and they kept pointing out one mistake we repeat like a reflex. We keep trying to drag the everyday idea of a thing down into the atomic world. And the lesson is simple. That move fails. Not because atoms are fake, but because our usual picture of what a thing is stops working. So let's build the answer from the ground up. No mystical slogans, no cartoons, just the real missing piece that makes matter feel solid. Put your hand on a table, press down. That feeling you get is so familiar that you never question it. Resistance? A stop. A hard limit. Your brain labels it as contact, like two hard surfaces meeting, like two rocks tapping. But at the microscopic level, that story is wrong. Because there are no clean edges down there. There are no tiny polished billiard balls. There are patterns, clouds, regions where electrons are likely to be. And when your hand approaches the table, what meets what is not? Matter on matter. It is charge structure, meeting charge structure. Electrons in your skin are negatively charged. Electrons in the table are negatively charged. And negative charge does not like to share the same region. It pushes back. That pushback is real. It is one big piece of what you feel as hardness. But if you stop there, you still miss the deeper reason, because you might say, okay, so it is just electric repulsion. And that sounds reasonable, but it is not enough to explain the stubbornness of solids. The no matter what, you cannot compress this easily behavior. For that, you need a quantum rule that is not a force. It is more like a law of organization, a rule about how identical particles are allowed to exist. Here is the rule in simple words. No two electrons in the same system can occupy the same quantum state. That is the Pauli exclusion principle. This is not just a detail for chemistry class. This is one of the main reasons matter takes up space at all. Because without this rule, electrons could all pile into the lowest energy arrangement. Atoms would be drastically smaller, and ordinary matter would be far less stable, potentially collapsing into much denser states. In other words, the world you know would not be stable in the same way. Now bring this back to your hand and the table. When you press your hand down, you are trying to push two huge crowds of electrons into overlapping arrangements. You are trying to force same here, same state on particles that refuse that option. Nature does not negotiate. It does not say, maybe just a little. It says, that configuration is not allowed. So what happens instead? The system finds another arrangement. But the more you squeeze, the harder it becomes to find allowed arrangements. The energy cost rises fast, and that rising cost appears to you as resistance, as stiffness, as solid. So the feeling of solidity is not your atoms slamming into table atoms like rocks. It is the world refusing a forbidden organization. It is quantum bookkeeping with consequences strong enough to hold up your body. That is the missing piece most people never learn. Solidity is not a simple substance. Solidity is a rule. Here is the part that bothers people. If electrons repel and if quantum rules block overlap, then what is touch? In everyday language, touch sounds like zero distance. Two surfaces meet. End of story. But at the atomic scale, touch is more like a standoff, a balance point, a stable spacing where pushing closer becomes extremely expensive. So yes, in a very real sense, you are always held slightly away, not by magic, by electromagnetic interaction and quantum exclusion. Your hand stops not because it hits a tiny wall. It stops because the energy required to force deeper overlap rises brutally, and your nerves interpret that as hard. That means the world feels solid because of fields and rules, not because matter is made of tiny, hard pellets. And once you see that, the next question hits you. Okay, then what is matter actually made of? Because the more you look, the less thing-like it becomes. And this is where a key warning matters. People hear a line like "atoms are not things" and panic. They think it means, so nothing is real? No, this is not saying the world is imaginary. It is saying your classical mental image fails. The image of little objects with definite properties at every moment, whether you look or not, like tiny planets in tiny orbits. Quantum mechanics does not support that picture. In the early development of quantum theory, physicists realized that trying to interpret atomic behavior as a definite electron path does not work the way classical intuition demands. In many situations, the theory gives you probabilities for outcomes, not a perfect movie of what really happened in between in classical terms. It also shows that at the atomic level, the act of observation cannot be ignored the way it can in classical physics. This is why one famous idea hits so hard. What we observe is not nature by itself, but nature as revealed through our method of questioning. Again, that does not mean atoms are fake. It means the atomic world is not obligated to match the categories your brain evolved for throwing rocks. The categories of solid little pieces and definite trajectories work great for baseballs. They fail for electrons. So, if atoms are not tiny hard beads, what are they? Here is the modern answer that connects directly to your title. Physicists use the word particle all the time. Electron particle, photon particle, Higgs particle. But there is a problem. Even experts switch between pictures depending on what they are calculating, and that can confuse everyone. A beautiful way to see this comes from a deep question. Is everything made of particles, or fields, or both? Charles Sabins explains that even in classical electrodynamics, there was a serious debate about what is really doing the work. Particles pushing each other across space, or fields filling space and carrying the interaction. In that story, Einstein preferred fields because he disliked action at a distance. Ritz preferred a particles-only picture. And the field idea traces back to Faraday, who treated fields as real physical structure, not just math. This matters because your question about solidity is secretly the same question. When your hand touches the table, is that a direct collision of particles? Or is it fields meeting fields? Modern physics leans heavily toward fields. And once you accept that, solidity starts to look like a field effect governed by quantum rules, not a collision of tiny stones. Here is the clean statement. In quantum field theory, particles are best understood as excitations of fields. A field is something defined throughout space, not a material fog you can scoop up, but a physical entity that can carry energy and momentum and produce forces. That does not mean the particle picture is useless. It means it is not the deepest picture. It is one convenient lens. The deeper lens is, fields are primary, and particle events are how those fields show up in detectors. Now connect that back to solidity. A solid object is not a brick wall made of tiny rocks. It is a stable arrangement of fields, electron fields in particular, organized around nuclei, filling regions, obeying exclusion rules, and producing electromagnetic forces. The table is not solid because it is packed with matter like a bag of marbles. It is solid because the field structure cannot be compressed into forbidden states without paying a huge energy price. That price is the pushback you feel. Yes. And this is where people get trapped by the wrong meaning of empty. When you learn that atoms are mostly empty, you picture emptiness as nothing is there. But what is actually there is not a little planet system with lots of blank space. What is there is the electron field in a low energy-bound state. It is spread out, it is real, and it can overlap with other electron fields. That overlap is literally what chemical bonds are built from. So the inside of an atom is not empty like an abandoned room. It is not a solid ball. It is structured probability and field intensity, and that structure produces real effects. Now we go one level deeper, because your title is not only about atoms, it is about reality itself. So what about truly empty space? What if you remove the atoms completely? Most people think vacuum means absolute nothing. Physics does not treat it that way. In quantum theory, the vacuum is the lowest energy state of the fields, not a simple void, a state, a physical baseline. So even if you remove every atom from a region of space, you have not removed the fields. You have placed them in their quietest configuration, and quiet does not mean dead. Because fields in quantum physics still have unavoidable baseline behavior, not because energy conservation is casually broken, but because the vacuum is not nothing, it is the ground state of a dynamical system. This is the moment where bad pop science says virtual particles pop in and out of existence. Be careful with that phrase. It is a metaphor that can help, but it can also mislead. The safer idea is the vacuum has measurable effects because field modes and energy differences can change when you change the physical setup, and we can test that. The Casimir effect is one of the most famous examples. Two uncharged conducting plates very close together in a vacuum. A tiny force appears between them, not because you turned on a magnet, not because gravity suddenly got strong, but because the allowed electromagnetic field modes between the plates are restricted compared to outside. Different allowed fluctuations, different energy density, a net force. In real experiments, you also have to control for ordinary effects, like stray electrostatics, but the remaining force matches the quantum prediction. Physics today describes it in exactly those terms. Boundary conditions limit which fluctuations can exist in the gap, lowering energy density there relative to outside, producing an attractive interaction under typical conditions. Britannica makes the same core point. The effect arises from quantum theory of electromagnetic radiation and the energy present in empty space, producing a tiny force. This is not philosophy, it is measurable. And once you accept that, the word empty never feels the same. Now, we can answer your title in one sentence. Reality looks solid because matter is organized fields, and those fields obey quantum rules that prevent unlimited overlap. In particular, the Pauli exclusion principle blocks identical electrons from piling into the same state, and electromagnetic interactions strongly resist compression and rearranged charges. That combination creates stability and volume. It makes solids stiff. It makes your hand stop. It makes touch possible. And beneath all of that, even the vacuum is not a featureless nothing. It is the baseline state of fields, capable of producing real forces in the right setup. So the missing piece is not a hidden chunk of matter you forgot to include. It is the invisible framework that your brain ignores because it cannot see it: fields and rules. Let's come back to the scary idea. Does quantum physics mean atoms are not real? No. These theories describe atoms with extreme accuracy and predict experiments with incredible precision. What they reject is a specific childish picture of atoms. The picture where an atom is a tiny object with a tiny orbiting bead following a definite path you could draw like a cartoon. In many quantum situations, that definite path story is not available in a clean way, and the wave and particle concepts can both be useful, but no single simple visual picture covers everything at once. That is the point. Not nothing exists, but your old categories are too small. Here is a simple thought experiment. Imagine you were made of truly classical tiny balls, hard marbles, no quantum rules, no exclusion. Then in principle, you could compress matter far more. You could push atoms through atoms like grains through gaps. The world would not have the same stiffness. But you do not live in that universe. In this universe, electrons are not little marbles. They are quantum objects, identical, indistinguishable in a deep way, and they obey exclusion. So they build space into matter. They force structure. They prevent collapse. And the contact you feel is your nervous system translating that invisible structure into a simple word: solid. Here is the final picture, stated in plain language. The universe is not a collection of hard things floating in nothing. It is a set of fields spread across space. Sometimes those fields are calm. That is what you call vacuum. Sometimes those fields form stable patterns bound together. That is what you call atoms. Sometimes those patterns lock into huge organized structures. That is what you call solids. And when two solids touch, what happens is not rock on rock. It is field on field, governed by charge and quantum rules. That is why reality looks solid. Not because matter is secretly filled in, but because the invisible rules and fields build a wall out of what looks like emptiness. So the next time you press your hand against a table, remember what is really stopping you. Not a hard edge, not a tiny barrier, a refusal, a rule. A deep, quiet law of nature that says identical electrons do not stack like coins, and fields do not let you cheat. That is the missing piece of matter. If this changed how you picture the solid world around you, leave a like. And if you want more deep dive journeys into what reality is really made of, subscribe. Because the deeper you look, the more the solid world dissolves into something stranger and somehow even more beautiful.